Good afternoon, all. First of all, thank you very much for everybody to join this first inaugural talk on quantum computing. It's really my esteemed pleasure to introduce our distinguished speaker, Professor Rajat Mittal. Professor is an accomplished scholar and associate professor at IIT Kanpur, who has made significant contributions to the field of quantum computing. So, without any further delay, sir, I would like to invite Professor Rajat to start your talk.
Thank you very much, Ashutosh, for a kind introduction. I welcome you all to the talk, and my task today is to convince you of why we believe that quantum computing has advantage over classical computing. So we will initially see why there is a reason that there should be a quantum computer, why should there be an advantage, and what we have seen till now. I hope it will be an introduction to you in quantum computing. This will motivate you to go further and study deeper in quantum computing. If you want to go into a serious study of quantum algorithms, you need to study linear algebra. You need to have some background in polynomials and math. It's basically a lot of math. So yeah, hopefully this talk interests you enough to go deeper into quantum. I would think of today's talk in terms of these questions which we need to answer. Why should there be a quantum entry? Is there a reason why people believed, and if you have been following the development from people have been trying to build a quantum computer from 1980s, we still do not have a what we would call a desktop quantum computer. So what's the reason why people are pouring in so much money into quantum computer? Why do they believe that there is a quantum advantage? I would like to give a glimpse of that. What has been the major results? In what sense quantum computing has fulfilled its promise? So what do we know certain things? If quantum computers, if we have a quantum computer, what sort of problems can we solve? What advantages will it give us? I will talk about that. And then a deeper question of actually looking inside a quantum computer and seeing that what physical property of quantum computation gives you the quantum advantage. So I would like to explain to you a toy quantum algorithm, and hopefully that will tell you why exactly quantum advantage is there. And then obviously the talk will finish by saying where we are and what do we expect from the future. What are the areas where quantum computing can provide speed ups? What are the areas where quantum computing's promise is not that much? So that's the kind of thing which we will discuss finally. So first question is, why people started thinking about a quantum computer? What, or another way to say it is, what exactly is a quantum computer? I will start with the story. And as they always say in the beginning of the movie, all the events in this story are fictitious, but the characters and the math is real. So I hope the concepts get clearer with this story. So you might know these two people: Richard Feynman, one of the giants of physics, and Alan Turing, giant of computing. And let's say that they were at a bar having beer together. They were enjoying their time. They started playing billiards. There is a billiards table in the bar. They're playing billiards. But, even though they were having fun, they are nerds. They are, one is a physicist, one is a computer scientist. They have to come back and talk about academics. So they start talking about computation. And being a physicist, Finman is, kind of confused about computer science, and he says, "What is a computer? What is computing exactly?" And then, Turing, being slightly young, says, "Oh, almost everything is a computer." And instead of clarifying the confusion, this made Finman more confused. What do you mean? What do you mean that everything is a computer? And then Turing says, any physical theory, any physical device can potentially be a computer. We are playing billiards on this table, and even this table could be a computer. And then Feynman is really confused. What does it mean that even a billiards table can be a computer? His example is, suppose I have a person, so you have a billiards table, so let's build some kind of a computational device using billiards table. Let's say you have a robot or a player who pockets one ball out of two every time they hit a white ball, they hit a colored ball with a white ball. Okay, so again, I'm assuming that there is a player or a robot. Their success probability is half, or they anytime they hit two colored balls, only one of the ball, exactly one of the ball, gets pocketed. If you know about this player, can you do computation? Can you make a can you do some computational task efficiently? It turns out actually you can divide by 2 using this. So it might be a very simple task, but again, what is computation? Computation is automated calculation, automation of your calculation task. Now, yes, you can take a pen and paper and divide, but a computer does it for you. So in this case, if you want to divide, let's say 100 by 2, you will put 100 balls in front of that player. He will hit all 100 balls with the white ball, and then you will count the number of balls pocketed.
Sorry to disturb you, sir. Maybe
Right?
switch off the video because there is little bit of a bandwidth issue.
Sure. Just give me a second. I have to, this Google Meet I don't use very often, so I have to
Yes, the video button
yeah.
you just toggle. Yeah.
Is this better? Yeah.
Yes.
Can you still see my screen?
Yes.
Okay, great. Yes. So so I was trying to make a point that even a billiards table could be a computer. For example, we can, if we have a player with certain physical property that he or she pockets one ball out of two, then we can actually use this phenomena to divide any number by two automatically. The point is automatically, right? So we just, whatever number we want to divide by two, we don't need to take a pen and paper and divide by two. We just put that many balls in front of that person. He hits that balls, and then we count the number of balls in the pocket. So any rule, any physical process can potentially encode a computation. And if that is the case, then we can use that physical rule to compute. Here, the physical rule was that the person pockets one ball out of two. Let's take another example. So let's take an example from a biological law, right? So let's say I have two insects. Again, these are, imaginary insects. They are not real insects. No such real insects are there. But let's say these are the insects which have rings on their body, as denoted by these blue lines. Let me just make a pointer. Yeah. So these blue lines, as you see, so they have rings on their body, and it is known that whenever they mate with each other, the offspring has, if the father had 2 rings, mother had 3 rings, the offspring is going to have 6 rings. So if the father had two m rings, mother had n rings, then the offspring is going to have multiplication of that many number of rings. If you know this about an insect, how can you use that insect to make a computer? What can you compute? Any ideas?
Product.
Exactly, right? So now you can multiply. What will be the trick? If you want to multiply, let's say 7 by 14, you will have to find an insect which has 7 rings. You have to find an insect which has 14 rings. You have to make them mate. Then you count the number of rings on the offspring, right? So this box where you make them mate, you collect the insect with the correct number of rings. This is your biological computer, which allows you to have to take a multiplication or product. So by these simple examples, what I'm trying to say is that any physical rule can be converted into kind of a computer. We encode our computation into a physical law, and then that physical law does the calculation for us. And this should not be surprising. Can you guess, in your classical computer, right, the one which is where I am giving this presentation, you are listening to it, what are the physical laws which are used, on which the computation is based?
voltages and
Exactly. Voltages, currents, Ohm's law, Kirchhoff's law, right? So all
yes, sir.
those properties of voltages and currents, we use them to make OR and AND gates and NOT gates. And from those gates, we build up higher and higher calculations. But ultimately, it is some physical law where we are able to encode small calculations. So, in other words, any physical law in some sense can be used for computation. And that's what Turing meant when he said that, anything is a computer. And now, obviously, Feynman only thinks about quantum mechanics. So he says, oh, if you can make computers, use any theory from physics to make a computer, why not make a computer from quantum mechanics? And that we will call a quantum computer. And then Turing, surely you're joking, Mr. Feynman. What do you mean? Why do you want to make a quantum computer using quantum mechanics? So now, now the Feynman, obviously, why is Feynman excited about making a computer using quantum mechanical properties? Because he thinks that quantum mechanics already has many, I would say, for the lack of better term, weird or magical properties like superposition, entanglement, right? So this felt weird for people. So if there are magical weird properties, probably you can encode more complex calculation inside these properties. And I will give you an example of how you can actually encode some computation there. That's for future. But more naturally, Feynman had another motive of talking about quantum computers. He wanted to simulate quantum systems. What does it mean? Simply put, let's say you have two electrons, you put them in a magnetic field, you have some interaction, and you want to know what happens to them, what is their state after 10 seconds. How will you calculate that? Now, one way is you have the initial state of electrons that looks like a big vector. You look at the action of it by a magnetic field, you solve some differential equation, matrices, vectors, and you evolve those vectors and figure out the final on a classical computer. That's going to be very expensive because the state is pretty large, these electrons. The evolution is not easy to compute.
So one of the ulterior motive of Feynman was that he wanted to make sure that he can simulate quantum systems easily on some kind of a device. A classical computer will take too much time because to record the state of an electron, it is a huge vector. To make calculations on it will take a lot of time. If there is a quantum computer, you can just have the electrons in that state, apply that magnetic field, and then observe what is the state. So in some sense, quantum systems are built to simulate quantum mechanical objects. And that's why Feynman was very interested in quantum computing. This was the initial reasons why people were excited about quantum computing. Anyway, so the story ends. People from 1980s got excited about quantum computing, but then still we haven't made a quantum computer yet. Let me tell you in nutshell what are the problems. The problem is manipulating small objects. We have learned this in our high school for quantum mechanics, that quantum effects are only visible at a very, very small level. All the big objects behave classically. So if you want to see the weird effects of quantum mechanics, where we can encode computation, encode nicer computation, then those devices, those systems have to be very, very small. And to manipulate these small objects, it's very hard. Let's say electrons, photons, or whatever. To take an example, you remember our biological computer? We had insects, and we were supposed to mate them to get to get our computer. Now, what could be the problems in a biological computer? First, can we have the input? Can we create insects with arbitrary rings? Can we force the required ones to mate? Can we apply the transformations which we need to apply? And then finally, can we count the number of rings? Can we get the output? And it's the same thing for a quantum computer. Can we create the input? Again, input means we want the electrons or photons in a required state. Can we keep these electrons and photons in this state for a long time? Second question, can we force the required ones to mate? Can we apply magnetic field on them? Can we apply different kind of transformations on them and still observe them continuously? They shouldn't leave the space. They shouldn't be as that unstable that they leave our computer. And then finally, once we have finished our computation, we have applied our effects on these electrons, can we finally measure the final state? So input, processing, output. All three are a problem because all these things have to be done for very, very small objects, which are really, really unstable. And this is the reason why building a quantum computer has been a challenge. Thankfully, I'm a theoretical computer scientist, so I don't have to worry about making a quantum computer. We are going to talk about, if there is a quantum computer, what can we get out of it? Okay, so what have we seen till now? Like, there have been, people have talked about quantum devices from 1980s, and then we are now in 2020. It has been 45 years of research. What do we know? Other way is there a good reason to build a quantum computer? Should our government, should American government, should Chinese government fund NASA, Google? Should they fund that much amount of money to build a quantum computer? So when I talk about quantum computing, I want to take it at a slightly general level, and let me talk about quantum devices, right? So any device which kind of exhibits quantum effects is a quantum device, and if we can harness those effects for our benefit, then we will call it a useful quantum device. And there are many such quantum devices already in the market. There are various applications for quantum effects. You can have quantum devices in metrology. You can have very precise lasers. You can measure distances very, very accurately using these quantum devices. You can communicate, you can securely communicate using channels where you are transferring quantum states. That's another very important area of applications. And I'm kind of highlighting these two because already we have these devices, we have hardware where these things are performed. Quantum devices, metrology, and laser have been there for some time. Even quantum communication, I just found out last week that we have shown quantum communication even in India. There are these labs in DRDO which have shown quantum communication between 80 kilometers and 100 kilometers of distance. So this hardware is already present in India. And coming to quantum computing, this is what this talk is about. What kind of things we can do for a quantum computer? In terms of what we have seen, using these lasers, we can do ultra precise measurements. We can find the distance much more accurately as compared to any kind of a classical scale. This was a very famous experiment done a few years back by Chinese scientists, where they were able to communicate between a body on the ground and a space and a station in the space. And this was done through quantum channel. So even at such large distance, they were able to do quantum key distribution. And this was not thought to be possible before. So this is again a very, very important milestone in quantum hardware. And then obviously you might have seen this photo, Sundar Pichai with the Google quantum computer, and this is the photo after which they showed what we call quantum supremacy, which basically means that they have come up with a problem which can be solved fast on a quantum computer but will take years on a classical computer. Is there a question?
Yes, sir. Sir, actually, I had a doubt.
Sure.
I wanted to ask, if quantum particles can go into a black holes or something like that,
Okay.
they move beyond space and time?
See, again, I'm not an expert, right? So the kind you are asking questions about physics now, right? Very deep theories of physics, which I don't think people have answered to these specific questions. I am a computer scientist. For me, I take well-established physical theories and see if I can use those to have a computational advantage. But if the electrons, once they go in the black hole, are they going outside of space and time? That's a question for physicists, not for me. So I'm not the right person to ask that question.
Thank you. Thank you, sir.
So yeah, I would like to make distinction between foundations of quantum mechanics and quantum computer. People physicists keep improving the quantum mechanical theories, its foundations, its principles, and all. Our job as a computer scientist is to take these physical principles and see how we can use them for a computational advantage. And why should there be computational advantage? That we will see in future slides. And all this kind of shows that whatever theory of quantum mechanics people have given from 1900s, it actually makes sense because we have been able to do so many applications on those principles. So yeah, there has been quantum key distribution at a long distance, quantum teleportation, where you send quantum states just by classical communication, and then obviously quantum algorithms. And I think most of you have heard of this Shor's algorithm, which actually factorizes numbers much more quickly than a classical computer, and hence potentially can break our crypto systems. So the reason why your credit card is secure, your internet communications are secure, those could be broken if we have big enough quantum computer which can factorize big numbers. If we focus on computing now, if we go to this smaller domain of quantum computing, which is more of my expertise, quantum algorithms, there has been series of algorithms which show that quantum can do something which classical computer will not be able to do or will be very slow in achieving. The first example was a small toy example, Deutsch-Jotze algorithm, and it was basically, it was not a natural problem. Its main aim was just to show that a quantum computer is more powerful than a classical computer. And obviously, I talked about Shor's factorization algorithm. It's a polynomial time algorithm for factorization. So the problem is very simple. You are given a big number n, and you want to find out its factors. This is a very hard problem at present for a classical computer. We don't know of any polynomial time algorithm, but a quantum computer can solve this in a polynomial time. And this is one of the main reasons why people are excited about a quantum computer. Another interesting algorithm is Grover's search. This is not an exponential advantage, but even here, it solves a very fundamental problem quite fast. What is the fundamental problem? You have n elements in a list. It's an unstructured list. It's not sorted. We don't know any structure of the list, but still we can search an element only by looking at square root of n elements. This sounds very weird, but yes, if you get familiar with the concepts of quantum mechanics, quantum computing, this can be taught in like a week. But what it achieves again is, given a list of n elements, I can find whether a particular element is there or not only by looking at square root n elements. This almost feels like magic, but this can be done. And since search is such a familiar concept, it is there in almost all industrial applications and any kind of algorithms you look at, everywhere you get this quadratic speed up. Instead of looking at n elements, you only look at square root n elements. So even though this speed up is only quadratic, since it's present at so many levels, this is a very, very useful algorithm. Similarly, in some conditions, you can solve linear system of equations. And again, this is a subroutine which is used in many applications. So this HHL algorithm is very, very famous. So there have been a lot of questions, lot of natural classical questions which have been answered on a quantum computer. And that's why we are excited about a quantum computer. Let's go to the main meat of this talk, where I will talk about why we think quantum mechanical properties can give us a quantum advantage. But before I start, I want to say one thing. Obviously, I was trying to convince you that a lot has been done in quantum computing already by now. If that was not quite clear, it's okay. The talk further ahead is independent of that, and I assume that you are here in the quantum computing research group, so you're already interested in quantum computing. But in any case, any other questions about what we have covered till now?
So maybe I have just one question.
Sure.
Once we know the Shor's and Grover's algorithm and the quantum advantage, how this is going to affect P equals to NP question?
Right. So can I assume that everyone knows P is equal to NP question?
May not be, sir, but you can explain. Means you can explain just in a very simple manner.
So let's just say that P are the problems which we believe which are solvable in polynomial time on a classical computer, and NP you shouldn't confuse it with not P. It's what we call non-deterministic P, but still they are problems which we don't believe can be solved in polynomial time. So I think 99.99% of the people working in this area do not believe that problems in NP are solvable in polynomial time. Though given a solution to the NP problem, you can verify it very fast in polynomial time. But anyway, that's not a topic of discussion for us. P are the problems which can be solved efficiently on a classical computer. NP are the problems which we believe already, which we have overwhelming evidence that it is hard to solve on a classical computer. The question is, what about NP or NP hard problems on a quantum computer? Again, there is, I would say, very clear, not very clear, but overwhelming evidence which says that we don't believe that quantum computers can solve NP hard problems in polynomial time. There have been many tries, but still, like this 3-SAT, this graph coloring, and all these problems. So the class of problems you can solve on a quantum computer in polynomial time is called BQP, and we don't believe that NP is inside BQP. It has not been proved yet. It can be true, but and obviously there are many other problems which we don't know in P, which are not in NP also. And factorization is one such case where we can get exponential advantage, right? And then there can be less than exponential advantage. So not doing anything about NP hard problem does not mean quantum is useless, right? That's just one place where quantum probably will not have any advantage. That's what I'm saying. But there are other avenues where quantum can be very, very useful. So should we take a look at a toy example and see why quantum provides advantage?
Yes, sir.
Okay. So this problem is called Deutsch's algorithm. Again, I would like to emphasize that this is a toy problem. This is not a natural mathematical problem. And the main reason we talk about this toy problem is because we want to say that quantum effects give us advantage in computation. This is the main motive of this problem. And you should view this in light of this assertion, right? I'm not showing that, quantum can do wonderful things in your life. I'm just saying, let's just first see, is there a problem where quantum can have, though problem is kind of make believe, but once the problem is there, is there an advantage, right? And there's an easy problem to show quantum advantage. That's why I'm picking it. But obviously, searching, factoring, now we know of many natural problems also where there is a quantum advantage. Okay, so what is Deutsch's problem? Suppose there is a function. The function is very simple. It takes a bit and outputs a bit. Okay, so the input will be either 0 or 1, output will be either 0 or 1. Okay, this function is given as an what we call an oracle or a black box. That means the function is hidden. I can ask a bit b and the oracle will tell me fb. So if I ask 0, the oracle will tell me f0. If I ask 1, my oracle will ask f1. Notice the task here is not to compute the function. The function will be computed by the oracle. What we want to do is find out whether f0 is equal to f1 or not. Okay, again, we don't want to compute the function. For compute the function, there is an oracle. We can always ask the oracle, give me the value of f0, give me f1. It will tell me. I just want to figure out whether f0 is equal to f1 or not. The issue is this oracle is expensive. If I ask it any question, let's say it charges me millions of rupees. So now, if you want to find whether f0 is equal to f1 or not, how many times do you need to query the oracle? What do you think?
2 times.
2 times, right? You will
Two
ask
times.
2 times, and then you will have to spend 2 million rupees. Correct? Is there a way that I spend only 1 million rupees and get the answer? Are you convinced that you can't do it? So if you take some time, you can convince yourself that, in one query to this oracle, I cannot figure out whether f0 is equal to f1 or not. It turns out, quantumly, you can do it in one query. And this is what I'm going to show you. How, by just querying this oracle once, you can compute whether f0 is equal to f1 or not. And this will give you an idea of how quantum mechanics has its advantages. But obviously, if you want to see how quantum computer does it, we have to know some basics of quantum mechanics, right? And I will not go into the detail of quantum mechanics. I will just talk about, what is input, what is meant by input on a quantum computer, what is the processing on a quantum computer, and what is a output on a quantum computer, and take the simplest examples of those so that I can describe the algorithm. But is the problem clear? Right. So let's learn a small bit of quantum mechanics. There are going to be 3 fundamental postulates relating to the input, processing, and output. First, postulate answers, what is my working space? How do I represent data? Or what is my input on a quantum computer? Second postulate answers, what kind of operations can I do on my data? Third postulate will tell us how can we observe the state of a quantum computer or a data. How can we measure data? How can we get information from the data? Okay, so let's look at these postulates one by one. The state space, to describe the state space, the easiest way is to visualize it as a vector. If you have one qubit is, so how do we represent data in a classical computer?
Just classical bit.
It's classical bits, right? The equivalent is a quantum bit, and the difference now is that I can be in state 0, or I can be in state 1, or I can be in some kind of a superposition of these two states. Again, this term superposition is loaded. What do I mean by superposition will become quite clear, but what it definitely does not mean is that I am in state 0 with some probability and I am in state 1 with some probability. Okay, because if that was the fact that, if you are in some state with some probability, if you're in some state with some other probability, if that was the only thing, then you will get what we call a probabilistic computer, and that is way less powerful than a quantum computer. So quantum computer is much more than having these states with some probability. It is much more than that, and that I will show you. Okay, so yeah, so what is a quantum bit? Its state could be 0 or 1 as a bit, and also it could be in a superposition. That means it could be in a mix of these two states, where alpha and beta are called amplitudes. They are complex numbers, and their mod square sum up to 1. And now for people who have looked at this, they will say, oh yeah, we are in 0 with probability alpha square, we are in 1 with probability beta square. I'm going to say that's just a consequence. That means this state, when I measure in a certain sense, then only I get that it is in state 0 with alpha square, it is in state 1 with beta square. There is much more to this state as compared to just saying that there is a probabilistic mixture of 0 and 1. Okay, so yeah, this is 1 qubit. This is in superposition. What is meant by superposition will become clearer as we proceed. And now, so now for 1 qubit, we had superposition on state 0 and 1. If we had 2 qubits, it would be a superposition over what? What do you think?
2 qubits.
2 bits, right? And what are the possible states of 2 bits?
The 4.
Four possible: 0001 1011. So then we get a superposition like that, where alpha 1, alpha 2, alpha 3, alpha 4 are going to be complex numbers. And then if you square and sum up, it will become equal to 1. Okay, so this is going to be our input states.
Sir, one more point. Even on the to add to this, we need to also talk about the Q trits also, quantum trits, where alpha directs 0 plus beta plus gamma. Again, the sum of the squares of alpha squared, beta squared, gamma squared is 1, right?
Mhm. So you can always talk about any n-trit system and
N-trit system, correct.
system,
Okay.
right?
Qubit is the
But
fundamental element.
right, and in the classical computer, we just have bits and multiple bits. That's why I can.
And the amount of information carried by this, by Lenovo's theorem, I mean, it tells exactly on the entropy, how much exactly. Theoretically, it is just 1 bit of data, but how it is being taken in the states.
Exactly. So this very good point. I will talk about this, that even though
That's
it might
something to assess
seem like
the
it is
information in quantum. Yeah.
right, right. Even though it might seem like this has a lot of information, but Hollywood theorem tells us that we can only get 1 bit of information out of this. So that's a very nice point, and I will make it clearer in the slide in few more slides.
Thank you.
Right. So this is how we represent data. And then in terms of transformations, again, remember that this is basically, if I want to represent the state, I can just write a vector which has alpha and beta. And then if I want to apply linear operators on a vector, those are matrices. So actually, your operations on this, or your processes which you can apply on the data, are all unitary matrices. That means there are 2 by 2 matrices which preserve the length of the vector. If you don't know what unitary matrices are, don't worry about it. Just think of them as special kind of matrices. One example is Hadamard gate, which takes 0 to state 0 plus 1 normalized by root 2, and 1 to 0 minus 1 divided by 1 by root 2. I have skipped the normalization factor because you can understand it if you see the total state, because the probability should sum to 1. So if there is a common factor such that these coefficients sum up to 1, you can figure out that constant, right? So I won't be writing by root 2, but this is the state is like 0 plus 1. So the amplitude on 0 and amplitude on 1 is equal. Here, the amplitude on 0 and 1 is equal in size, but its phase is different. Okay, and these two are very different states. Again, to make the point about probability, if you just want to look at the probabilistic interpretation, This is a state which is in 0 with probability half, 1 with probability half. This state is also in 0 with probability half, 1 with probability half. So then these two states should be equal. But that's definitely not the case in quantum. We will see that these two states are very different. And this is the reason why our Deutsch algorithm will work. Okay, so once again, we had vectors as our states, this superposition, and then we can apply processes on them like this Hadamard gate. And like one bit was 2 by 2 unitary matrices because my vectors had length 2. For 2 qubits, I will have a vector with length 4, so I will have 4 by 4 unitary matrices as the processes. But even if this unitary matrix is not clear, just remember this gate, the Hadamard gate, which I can do in a quantum computer. I can take 0 to 0 plus 1, 1 to 0 minus 1.
So sir, can we say that when we apply these gates twice, the state will be back to same?
Yes, you can calculate that by linearity. If you apply Hadamard gate again on 0 plus 1, 0 will get to 0 plus 1, 1 will get to 0 minus 1, and then amplitudes of 0 will add up. You will get a 0. You will get just the state 0. Yes, by this we say that Hadamard gate is reversible. It's an inverse of itself.
Yeah.
Okay, so we now know what is the input, how do we process, but what is the measurement? How do we figure out what is my state? Remember, my state was alpha 0 plus beta 1. If I'm given an electron with the state alpha 0 plus beta 1, does it mean that I can get alpha and beta? No, I can't get alpha and beta from an electron which is in state alpha 0 plus beta 1. I can only do projections onto a subspace. Again, this is a more general term because we have vectors. We can project onto a subspace to measure. What it means for us simply, if you are not familiar with linear algebra, for 1 qubit, the standard measurement is you measure alpha 0 plus beta 1 in 0 and 1 basis. You will have alpha square probability of getting 0. You will have beta square probability of getting 1. But this is only one kind of a measurement I can do on this state. There are other ways to observe this state too. In the simple example, I will only be concerned with this kind of a measurement. But so this is the important measurement now, but please remember this is not the only measurement possible. Right, and this point I have harped on multiple times. So this probability, this alpha 0 plus beta 1, I get 0 with probability alpha square and 1 with probability beta square is a consequence. It is definitely not equivalent to this state. This alpha 0 plus beta 1 is not equivalent to being in 0 with probability alpha square, being in 1 with probability beta square. Okay, so let's just see what I mean by this, what we can do with this small quantum mechanical principles. I would just like to explain a small experiment. So this is called a beam splitter. What it means is that if I send photons one by one on this beam splitter, half the time I will detect a photon here, half the time I will detect a photon here. Right? So if I say that my photon goes to detector 2 if it is in up state, and it goes to detector 1 if it is in the horizontal state, then you might think that, oh, this is just a photon which is in half vertical state and half horizontal state. Correct?
Yes, sir.
That could be an explanation. What I'm going to show is that explanation of physics is not good enough. Okay. So again, this is in some sense state vertical plus horizontal, or you can think of this as 1, this as 0. So 0 plus 1, whatever way you want to think of it. But yeah, what you have physically observed is when the photons go here one by one, half of them are detected here, half of them are detected here. So a person who is saying, oh, there is nothing special about quantum computer would say, oh yeah, it is in vertical position with probability half, it is in horizontal with probability half. It turns out that if I just replicate this experiment where, we have instead of one beam splitters, two beam splitters, and this is a mirror, this will always reflect. Okay, so you see a difference between a beam splitter and a mirror. Mirror always reflects. Beam splitter can potentially reflect or refract, right? So now, if my photon was in half zero, half one, it would, half of it, half will go here. Then again, half of the half, that means 1/4 will go here. Again, half will go here. This half goes here. And then once again, half of half goes up. If the probabilistic interpretation was true, I should see electrons, half the electrons again at detector 2 and half the electrons at detector 1. Once again, if we believed that our world was probabilistic, this photon was nothing but, half in horizontal state, half in vertical state, then again, from half you get 1/4 here, from half you get 1/4 here, and at detector 2 you should get photon with half the probability, and same here. Sorry, is there a question?
So actually, you meant that I mean the probabilistic idea was I mean it didn't carry the probabilistic idea. Like like it has other states. Like it isn't in only two states, right?
Right. But what I'm saying is that generally when you look at that quantum state, people tend to equate it with a probabilistic state.
Yes, sir, I got you. Sir. Yes, sir, I
And
got you.
and I just want to emphasize that that is
It
not
has
good.
more than probabilistic ideas because
Yes, that
if
is not
we
good.
yes, sir, yes, I got you.
And physically, when you do this experiment, the electron never appears at detector 1. It is always at detector 2. And this
Detector
has
two, yes,
been
sir.
done physically.
Yes, sir, yes, sir.
You
I
can read
understand.
about it. So this is a proof that your probabilistic interpretation was not correct. Okay. So now this, so then when we look at alpha 0 plus beta 1, we should think of it as in superposition with amplitudes alpha and amplitudes beta. Now, with that, what can we do? We can solve the Deutsch problem fast. Do you remember Deutsch problem? We had an oracle which gave us value of function on 0 or 1, and you wanted to find whether f0 was equal to f1 or not. Is that okay? There was a black
Yes, sir.
box, there was an oracle.
Yes, sir. Yes, sir. Got it, sir.
Yes, sir, we are with
Great.
this.
Right? And I promised you that I will show you just by one query to the oracle, I will solve this problem. Correct? How do I solve it now? Now I know quantum mechanics. How do I solve it? Point is, wait, I don't know what is the oracle in the quantum case. What does it mean? You might think it's straightforward. Classically, I had an oracle. When I send the state B, I get the output FB. Now, if I get set state cat 0, I should get F0 as the output. If I set state 1, then I should get state F1 as the output. You would think that that should be your quantum oracle. Unfortunately, quantum mechanics prohibits you from making such an oracle because this oracle is not reversible. Quantum mechanics is reversible. What do I mean? Suppose F0 was equal to F1, then irrespective of the state on the left, I will always get the same output. That means knowing the output, I can't reconstruct the input of this oracle. And this is something which quantum mechanics does not allow. You can never build an oracle like that. So if F0 was equal to F1, then this oracle is not permitted. So what we do is we will modify our classical oracle to have the same capabilities, but make it reversible. And now let me just tell you that when I make the oracle reversible, this is not cheating. This is something which is allowed classically also. I can give this reversible oracle to to a classical computer, and still it will need at least two queries to find out whether f0 is equal to f1 or not. Okay, and actually there is a universal construction which takes any circuit and converts it into a reversible circuit. So you can think of the new oracle in the classical case also. So I'm not hiding anything under the rug. you take an oracle. I just explained that B to FB oracle because it was simpler to understand. But if you look at this reversible oracle, it does the same thing. You give the bit and you have W as the answer bit. What happens is this bit remains as the same and the answer is XORed to the W bit. Is everyone familiar with this XOR symbol?
Yes,
So
sir. Yes, sir.
this is exclusive OR. If both bits are same, then it is 0. If both bits are different, then it is 1.
This one. Yes, sir.
Right? So if, in other words, if W is 0, then this state will be FB. So this is exactly like the previous oracle if W was 0. So B will remain B and here you will get FB. And this is reversible. Knowing here, I can always reconstruct the state here. Okay, so this is my classical oracle. Now I can convert it into quantum states, and this is going to be my quantum oracle. Question?
Yes, sir. I absolutely understood that.
Okay, so this is what I meant. If you feed the state 0, you get FB here. Whatever be or B, if you want to calculate F0, you give 0 here, keep the state as 0, you will get F0. If you give 1 here, 0 here, you will get F1. But now we are in the quantum world, and if we only feed 0 and 1, then we are doing classical things. Let's do some quantum things. What if I give state 0 plus 1 by root 2? You know the thing which I get by applying Hadamard. What will happen now? By principle of linearity, I will get state 0 F0 and 1 F1. Again, this does not mean that I have access to both F0 as well as F1. It is known, we have a proof that we can't get both F0 and F1 from this state. So this is not like a parallel computer. It is not like we have computed F0 as well as F1 in parallel. It is just a mathematical representation where both F0 and F1 are appearing. There is no way to get both F0 and F1 from this state. But quantum mechanics tells us if we start with a superposition, we end up with a superposition. But we still don't have F0 or F1. If we measure it, we will either get F0 or get F1, not both.
Yes, sir. But I mean, initially it wasn't like we have two probabilities, but now we can prove that F0 is equal to F1.
No, we can't.
With quantum also.
With quantum, we will see. Still, it is not clear how do we apply quantum to figure out whether F0 is equal to F1. This
Okay,
mathematical representation has both, but how do we compare whether it is equal or not? We don't know.
Yes, sir. Got it, sir.
So for figuring out whether F0 is not equal to F1 or equal to F1, we need another trick. Okay, so first trick is this simultaneous computation. If I give this state as plus, then in my mathematical representation, I get F0 as well as F1. The next trick is phase trick. What does it do? Remember initially when I had a bit here and I had 0 here, I got FB. What phase trick does is if I give a minus here, and you can check this by linearity, my answer is computed in the phase. It is not computed inside the sketch symbol, it is in the phase. That means if B is 0, then I get a plus 1. If B is 1, then I get a minus 1 times minus state. Okay. So now I have two tricks in my hand. One is simultaneous computation, which is this plus to 0. It gives me 0 F0 plus 1 F1. And this phase trick, which means that instead of computing the answer here, I can compute it as a phase. So let's see what if we merge the two. So if we give plus and minus, then I get the minus state back, and this is in the superposition. So remember, Previously, with the simultaneous computation, it was cat F0 and cat F1. But since we applied the phase trick, I get the answer in the phase and not as cat. So I was supposed to get this, but since this is minus now, I am applying the phase trick. I get -1 F0, -1 F1. And my claim is we are done. And you might ask why. So let's see. This is the state which we have gotten. And now you might be able to see that we can compute whether F0 is equal to F1 just by applying a simple gate. I will give you a chance. Can someone say why can we figure out whether F0 is equal to F1 from this state? What if F0 is equal to F1? Then what state is this? This is the state which we have seen. It is the plus state. If F0 is equal, if F0 is not equal to F1, then it is a
It's a negative state,
minus
sir.
state.
Minus state.
Minus state, right?
Yes.
This state is plus state if F0 is equal to F1, and this is a minus state if F0 is not equal to F1. So now can you think of how do I finish it? How do I figure out whether F0 is equal to F1 or not? So I know that I did this computation and finally I have either a plus state or a minus state. How do I figure out whether I have a plus state or minus state?
Can put the Hadamard gate.
Exactly. We just discussed that Hadamard is the inverse of each other. So we apply Hadamard
Yes,
on
sir.
it.
Hadamard's gates, yes, sir.
Yes, when we apply the Hadamard, plus will get converted into 0. Minus will get converted into 1.
One, yes.
Right. So if we we apply Hadamard and then measure. If we get a 0, that means F0 was equal to F1. If we get a minus, then if we get a 1, that means F0 was not equal to F1. Important thing to notice here is, even though all the time it looked like we had F0 we had F0 and F1 both, after the algorithm, we don't know the value of F0, we don't know the value of F1. Actually, if you think about it, we still have only one bit of information about the function, which is whether F0 equal to F1 or F0 not equal to F1. But so yeah.
But we didn't get the value of F0, F1. Like we can
did
predict.
not. Yes, exactly.
Yes. We just only proved that F0 is equal to F1. With
Or
one,
Yeah. That was the actual question, actually.
that was the actual question. So
absolutely, sir. Yes,
yes,
got it.
the information, the amount of information did not change. The kind of information we could get changed.
Yes, sir. Like initially we did it for 2 times. Now we can do it in 1 time. Like we can prove
One.
that. Yes, with 1 time. Yes.
One, exactly. And now, if all this calculation seemed slightly complicated, let me try to give a physical interpretation of this algorithm. Okay, so the final Hadamard gates collect the amplitude. In other words, the amplitude of 0 becomes -1 to the power F0 plus -1 to the power F1. Now, if F0 was equal to F1, then we get these amplitudes add up. This is the constructive interference. If F0 equal to F1, these two amplitudes will add up. I will have sense of a constructive interference, and I will only see state 0. If F0 is not equal to F1, these amplitudes will be different. They will cancel out. So I will have no amplitude on 0. That means I will see state 1. This can't happen with probability. This cancellation of probabilities never happens. In the probabilistic computer, things only get added up. And that's why quantum computer is fundamentally different from a probabilistic computer. Okay. So again, nothing better than a picture. So let's look at a picture. What happened was, so in some sense, you should view this as amplitude as my input. Now, when I apply Hadamard, what will happen? It will get divided into 2 parts.
2 parts,
0
yes,
plus
sir.
1. right? So I have now two states, 0 and 1, correct?
Yes, sir.
Now, when I apply the function, this these two parts, if f0 was not equal to f1, there will be a different phase applied to these parts. So what I will get is something like this. You see that there is a phase mismatch. What the oracle does is apply a phase on these waves according to whether they are zero wave or one wave. So if f0 was not equal to f1, the phase applied is different on these two. There is a phase difference between these two. And then when I collect the amplitude using Hadamard, I get nothing because this is a destructive interference. On the other hand, again, I start with 0, I create 0 plus 1, which is in equal superposition. If f0 was equal to f1, the amount of phase applied on these two will be the same.
Same. Yes, sir.
That means they will still be in phase. And that means when I interfere, there will be a constructive interference and I will get all the amplitude on Z. Okay, so probably Deutsch was a physicist and he had this kind of an interpretation in mind, and then he could come up with whatever I showed you. But the point is, I can create this superposition, I can create a phase difference, and then using constructive and destructive interference, I can get a pattern which is not possible for a classical computer. So why are we, what are the promises at this point, right? There were some promises in 1980. We have seen some things which have happened. What kind of things are there for future? Again, we have computers, we have many companies which are investing a lot of amount of money, probably because they think there are many dimensions where quantum computer can be useful. One of them is optimization. This is a slightly different model of computation. It's called adiabatic computation. It is again quantum computation, but it does it in a more physical sense. And if you have heard of D-Wave company, they make computers in this adiabatic computation sense. These computers seem to be good for solving optimization problems. Not all optimization problems, but certain kind of structured optimization problems can potentially be solved using these kind of adiabatic quantum computers. And if you want to talk about next 5 years, it seems if you want to see some applications, probably they will be the applications in this particular domain. This is kind of an adiabatic D-Wave quantum computer. Another approach, another people people are excited about is quantum machine learning. When you talk about quantum machine learning, there are different things. What kind of data do I have and what kind of algorithm I'm applying, right? So the general idea of quantum machine learning is this box where I have the classical data like a classical machine learning algorithm, but I want to apply quantum algorithm to get things fast. So even though all four are valid ways to look at quantum machine learning, this is the more popular one. Classical data, quantum algorithms. There's also called enhanced with quantum computer, machine learning enhanced with quantum computing. The problem is with this area is there are nice applications, but it requires a full-fledged universal quantum computer. We don't have that yet. I would say still the time frame would be kind of 10 to 15 years, and that's also I'm not sure. So before we get a big enough quantum computer with lot of quantum bits, these applications are not going to come into practice. These are things which use XTL algorithm, Grover search, and things like that. So the building blocks are again the things which you will see in a basic quantum computing algorithm course, but then you build upon that to show applications in machine learning. There are sampling, annealing techniques which can, like adiabatic quantum computer, can also help there. But yeah, so this is an area where people have shown many results, but I think it is far from having any practical applications yet. Probably at least 5 to 10 years in future, we will see some applications. And whenever you see such algorithms, major quantum algorithms to solve magical problems, I would say you should be cautious, because most of the times these are not algorithms, they are heuristics. There are no provable guarantees. We don't know whether, in all cases will they work, or there might be just be evidence that they are working, not a mathematical proof that your algorithm actually works. Many a times they hide the complex part in state preparation. So they will say that they will start with some magical state, but how do you create that state? That is not clear. So in some sense, their algorithm is not complete. They don't. So a quantum algorithm, you have to describe it. You have to start with all zeros, come up with an input state, apply the processing, and then measure the output. If you start with a weird state which people don't know how to prepare, then it's a cheating in some sense. And there is literature now in last 2-3 years or last 5 years where these things have been done. And then also there are some quantum machine learning tasks which were shown that, oh, we can do this quantumly. And recently, with the work of Tang and Scott Aronson and all, it has been shown that probably you can even do it classically. So if given a nice sampling procedure classically, you can do all those magical things. So when you read a quantum machine learning paper, or actually a quantum algorithms paper in recent years, you should be careful that, actually it has theoretical guarantees. There are no hidden steps, and there are no equivalent classical algorithms. So these are the kind of things which are going around, because the field is obviously new, and we are not mature enough to have clear quantum algorithms. And then obviously, if the algorithm requires full-scale quantum computers, then it is not practical at this point of time. Right. So I will conclude. By encoding computations in a law of theory, we can create new models of computation. This is like quantum computers, DNA computing. So many places people have realized this idea that if I can encode computation in some physical law, I can probably compute faster, or I can compute differently. It's the same idea which works for a quantum computer. In case of quantum computer, we get the power, we can encode our computation and get answers fast because of these properties like superposition and entanglement. You saw superposition. Even entanglement was in some sense hidden inside our algorithm, but I didn't talk about it, probably in a more advanced course. This could be explained, but yeah, these are the two fundamental properties, physical properties, which are the reason why quantum computers are more powerful. A very important point, it is not a cure-all solution. There are particular fields where quantum computing has applications now. There are some fields where we believe that quantum computers will have applications in 5 or 10 years. And there are some problems where we believe that quantum computing is not going to have an advantage. For example, let's say solving 3-set. For example, let's say solving any NP-hard problem. You can get a quadratic advantage from growth search, but you would not potentially get an exponential advantage. We don't have a proof of that yet, but overwhelming evidence from complexity theory that, yeah, we probably can't solve NP-hard problems efficiently on a quantum computer. So yeah, it has immense potential, but it is not a one-step solution for all the fields. And by this presentation, I might have convinced you of this two things. One, a quantum computer is not a parallel computer. Remember Hollows bound, we can't get 2 bits of information. Even though the state looks like 0f0 plus 1f1, we can only get 1 bit of information out of that state. So it's not a parallel computer, and also it is not a probabilistic computer. It is very different from a probabilistic computer. Thank you. I would be happy to take more questions.
Okay. So, sir, I was just, as far as what I understood is it looks like that there's not only one particular, you can say, law in nature which can be exploited. So the quantum computer itself could be based on different principles. And then the algorithms, like one algorithm we discussed, algorithms would be exploiting those principles. So is it like, can we say that the there cannot be any general purpose quantum computer. It's like where you can just run arbitrary algorithms and get a generic speed up. Means can this, is this kind of understanding would be clear? I mean, would be feasible to think in future, or this is not correct?
No. So think of it in the classical case also, right? You can argue similarly that you have so many physical principles in electronics and electrons and photons. Then that means we can have different computational devices, but still the idea was that we had something called a Turing machine, right, which encodes computation on a classical device. Similarly, we had a concept of quantum Turing machine, and people showed that quantum circuit model is equivalent to a quantum Turing machine. That means whatever kind of computations you can do on a quantum device, they can be simulated efficiently on a quantum Turing machine or a quantum circuit model. So like we have a general purpose classical computer, we can create a general purpose quantum computer if it has enough gates.
Okay, so that means yes, that's a feasible idea, and we can. But as of now, when we saw that there are couple of algorithms, like whenever it comes to the algorithms for the quantum computer, we can always count them in hands, like fingers. Like okay, Shor's
Correct.
algorithm,
Correct.
five,
Correct.
six algorithms, basic, and then the factorization and searching algorithms
Mhm.
and all that. So what it makes for a person to, let's say, think about a new algorithm to solve is, so if somebody wants to be, let's say, the research, do the research in quantum algorithm, creation of new quantum algorithms, what that does that precisely mean?
Yeah, so that's the what you have observed is very important, right? That even though with 40 years of research, we have a handful of algorithms which are new. What it shows is that it is very hard to think quantumly. Quantum intuition doesn't come to us naturally. That means if you want to develop quantum algorithms, it needs an in-depth study. It is true about every field, but since the quantum intuition is very weird, it doesn't come to us naturally. We really need to devote a lot of time in understanding the background and getting a feeling of what quantum computer is. What are the laws? What does it mean that a quantum algorithm is successful and it is not? So yeah, it requires a lot of understanding of math, and that's why we go into this rigorous notion of mathematics where we can formally figure out whether a quantum algorithm is working or not working. But there to come
So
up with a new idea, it has been a challenge.
yeah, so provided that, what would you suggest, like if somebody wants to means, because it's just like some of the initial thoughts related to quantum computing are really sometimes discouraging, that somebody will, who is starting, you will think that, say, that's probably I will not get. I mean, there are no low hanging fruits, so I can just do
Hmm.
some research and do this. So in that direction, what do you suggest, that what kind of work people can start looking initially, at least, to make their career in this direction?
So one of the, I think the most basic thing you have to do is probably take a quantum computing course, a basic quantum computing or a quantum algorithms course. It could be a Coursera thing, or there is this book by Nielsen and Chuang. I think it's a very old book, but still it's an excellent introduction. As a like the way you have formed this interest group, one of the thing could be a reading group for Nielsen and Chuang. If you all of you are more computer science minded, then there is a book by Laflamme, Mosca, and one more author. Even that book is very nice. So you can have a reading group where people present every chapter one by one, and then you discuss.
My next question is, because see, I'm trying to understand from this large group, because there are only 22 people and but we have 180. I'm just trying to figure it out, because at the end of the day, the very, you can say, deep level physics and math and algorithmic development may not be the cup of tea for everybody. So, for example, nowadays, I mean, as you said, the QML, correct? So, and quantum programming, means quantum programming is nothing but just you do a course and you understand how to how to make a circuit in quantum this thing. But again,
Correct.
it's like if there are 10 algorithms, you just develop those algorithms in quantum program and just see how they work. What
Mhm.
beyond students or people can do, like when it comes to quantum programming, and means without much knowing about all the physics. First of all, is that a feasible idea, that without not much knowing about the lower level details and work on as a quantum programmer? Just like we say that I'm a Java programmer. Can somebody in future, in down the line 5 years, say that, see, I'm a quantum programmer, quantum computing programmer, and see, he is just happily know 3 or 4 languages where he makes program and try to utilize that in some of bigger softwares and make it useful. So is that a correct direction, or what do you say, sir,
So
about that?
depending on what you want to work on, if you want to work on quantum algorithms, like me, I would say that all very basic knowledge of physics is needed. I don't know almost anything about quantum mechanics. We take out few of the principles, which are these postulates, and after that, it becomes a question about how to model these in linear algebra terms. Now, second question is in terms of low-hanging fruit. Obviously, there are many people who are simulating, the known algorithms. There is this QuizKit, which is an open tool by IBM, and uh, there are papers. There are other. Amazon also has some service for quantum, so where you can run your quantum programs. Once you have a basic course, once you know how to make a quantum circuit, you can try writing up programs on that.
So, sir,
Yeah.
further to that question, if somebody is, let's say, just simply testing its quantum programs, but then for that he might have already created an algorithm, correct? So then when he's programming, so can you give some simple example, because it is still not very clear to me, that as a professor, can I ask some student that, okay, create a program for this, go and create an algorithm and write a program and test it? What can I say?
No, see, for research, you have to see at this point, after one talk, I can't tell you a research problem.
No,
Once you
not
do a
research
course,
problem. It's like, let's say for the quantum computing course itself. So let's say I'm taking a quantum programming course in bits, which I'm planning, and for that I want to give different assignments to the student that create write your own quantum program. So
you
what
can you
does
can
that mean?
you can do a 2 or 3 bit Deutsch problem. You
Okay,
can ask them to create Grover search on 8 inputs bits. You can do a quantum teleportation circuit. You can
okay.
you can there are
So
many
that
many
means
basic.
the some kind of variations of the existing algorithms what we know.
Right. And see, again, even though my basis is algorithms, that's a very, very narrow area. Once you read about quantum computing, even in computer science, you can talk about cryptography, you can talk about communication, you can talk about different models where quantum is applicable. So there is this quantum query complexity, which I study. Then you have quantum algorithms, then you have quantum complexity classes. So it's a huge area. Developing a clear-cut algorithm is a very small part of it.
Yes. And so
But
from
all those
from
areas open
quantum,
up, all those areas open up once you have your basics right. Then,
yes.
right? So,
And so from post-quantum cryptography perspective, means I teach here cryptography and we have done some, but what we found is like post-quantum cryptography is all about, is like
that
what you have already clarified, is like, see, anyhow, just finding the other hard problems for which as of now the quantum algorithm is not known, and then you are safe. So
yeah,
so even
most
if the
of the
quantum computer comes, those algorithms are not breakable, or those hard problems are not breakable, unlike factorization. But there is no quantum as such. It's just like cryptography only.
yeah. So there is, as we like to say, there is no quantum and post-quantum cryptography. It's
Yes.
mostly finding out classical problems which are hard for a quantum
Yeah.
computer.
Yeah.
That is the bulwark of post quantum cryptography. There are a few quantum techniques, but since that those are this they are symmetric encryption, so
Yeah, so
I don't
like
know.
QKD and all, it's like quantum cryptography means like secure key exchange using
Yes,
quantum channels, and so that
correct.
is that is probably somebody can do it. But post-quantum cryptography is certainly just a cryptography. You can say advanced
Yes.
cryptography.
Yes, that is true. That is true.
Thank you very much, sir. Means I really asked a lot of questions and clarified my doubts.
The practical obstacles for a quantum computer are stability and scalability. That means, can you keep the states in the required state for a long time? When I say long time, I mean 1 nanosecond, 1 millisecond, or something. And scalability is that, in the classical case, going from 20 bits to 40 bits means, you just double up your resources. That's not the same for a quantum computer, because you need entanglement. And that means scalability is much harder to go from, decoherence. So going from small systems to big systems is very, very hard. The 80 kilometer thing I was talking about was a quantum communication thing. And even in quantum communication, stability would be a problem. They have these amplifiers which keep the state alive in small distance. So if the distance is more, theoretically it's not a problem, but practically it is a big problem. And that's why this satellite to ground communication is a major, major breakthrough in QKT. Thank you. It was my
Thank you.
pleasure. I really liked it to interact with
Thank you,
all of
sir.
you. Thank you
Thank you.
for this. Hopefully we will see you again.
Thank you.
Bye.
Thank you. Once again, thank you very much, sir, from QCIG Group.